welcome back. So let's dive deeper into the set of actions that you could take that ensures governance is happening correctly. So one of the first is what's called as drift monitoring. In fact, I would say this is actually required irrespective of whether you are regulated or not, whether you're legally mandated to do change management and drift monitoring. So okay, scratch that. Let's start again. Welcome back. Let's take a look deeper into the actions which are available to you that allow you to ensure governance is happening correctly of models. Now, the first such action is called as drift monitoring, or activity is called as drift monitoring. In fact, I would say that irrespective of whether your industry is actively regulated by laws of the land or not, if you do model management or if you do model building, you should also do change management. You should also be prepared for change management, and drift monitoring is one of the most important activities for it. So, what is drift? As the imagery suggested, uh, an automation system which goes, in a straight line is expected to remain in that straight line and not deviate from it. But if it does deviate, and if the deviation is something that's persistent, then you want to be alerted about it so that you can take corrective action to ensure that it comes back to that line. In the world of autonomous driving, the consequences are disastrous. We can all imagine and visualize that. In the case of ML driven systems, more generally, the consequences are equally significant. Maybe not disastrous, it varies by industry, but the consequences are significant. So the more drift happens and you don't detect it, the more you are susceptible to take suboptimal decisions and, in fact, incorrect or extremely wrong decisions as well. So you've got to be really careful about this. So the persistent deviation is what is important. There are small deviations which are possible and which are also feasible and which might also be tolerable, right? So we're not talking about those. We're talking about persistent deviations in the functional performance of a model over a period of time. So you might have launched a model for fraud detection, and it works superbly. So you've got all the optimization done, the incentives are worked out, the objective function is maximized. So that rolls into production on day one. Within 6 months' time, your company is actually hit with multiple frauds. The question comes back to you on why did your model not capture that? And that could have been because of multiple reasons, right? Input data could have changed. The model power may not be adequate anymore because the business has become more complex. Hyperparameters have not been chosen optimally. Those were optimal 6 months ago, maybe not anymore. Model choice is improper potentially. So the power of a model is basically a combination of what kind of representations of the underlying mathematical behavior are possible and what are the parameters that control these representations and how much have those parameters been tuned, right? So that power in general could be inadequate because of various changes that have happened. Just to contrast, right, software engineering systems, which are highly deterministic, consistent systems, rarely drift. So once they are certified to be working correctly, you would not expect a deterministic software system to actually say that I can no longer handle that situation I used to handle before. So if it happens, usually because of a change, then testing, especially regression testing, would capture those and would flag those kinds of instances. And if regression testing has passed those tests, which means that the behaviors have been consistent, and then you would not expect the software to magically stop behaving correctly for functional reasons. So that's what makes this different from conventional software engineering. What are the types of drift that's possible? So there are essentially three types of drifts. If you really think about ML models as black boxes, there are a bunch of inputs, it's learning a bunch of representations, or rather it's learning a representation that links these bunch of inputs to an output, both of whom are visible. Then these representations can be many, based on what the relationships between the input and output are, fundamentally, three things can change. Input can change, the output can change, or the relationships itself can change. So that's how drifts happen. There's input drift, which means the input distributions are changing over a period of time. So the mathematical way to say it is the probability distributions of features like X are changing over a period of time. So the example here would be loan applications typically come from um, the salary demographic in India. Let's say that was the starting point when the model was built for the first time. Salaried class typically starts from 23 and then goes further up till 60 when retirement typically happens. Now suddenly loan applications have started to come in from a completely different age group. So maybe it's coming from senior citizens who are not salaried, and that's a age uh, that's a behavioral pattern that you're not used to as a model. So then the impact of the model is that the model might struggle to make up its mind on that group of people because it's seeing those input patterns for the first time. So that's input drift. Now, by the way, models struggling for output or struggling with those unseen input patterns, that's English language, right? So what actually happens in the back end? The model might not give you a clearly separated outcome, right? If it's a regressor, for instance, the regressor might not give you a clear answer. It might give you an in-between kind of an answer. If it's a classifier, the classifier might still produce an output, but the confidence attached to it might be very low. So those are all ways in which it manifests, like how a model struggles with something that's not seen before. That's input drift. Label drift, or also basically output drift, is the target column or target features that you're learning to predict is itself changing. So the distribution of targets are changing. So for instance, in a fraud detection model, the fraud rate is now decreasing over time um, because there are fewer fraudulent transactions. And that could be because of various reasons. It could be because of strong authentication principles that have obviated the need for fraud even before your fraud model gets invoked, right? Etc. etc. So if that's not known to you as a model developer, the model might actually over predict fraud based on the old label distributions and all based on old historical data. So that's an impact. The third type of drift that's possible is a concept drift, which means here the relationship between the input and the output used to be in a certain way, and now that relationship has now changed. The pattern of the relationship has changed. So here, the probability of the target being something given the inputs, so probability of y given x, that joint distribution has changed, and therefore the model that you have learned is no longer valid. So the fraud patterns, if you look at the fraud detection example, fraud patterns have now changed to include new behaviors, and the new behaviors are driving the new fraud, which means input has changed, new behaviors, new fraud, which means new types of outputs are possible, new types of fraud are possible. In this kind of a scenario, the fraud model or detection model that you've built may not even be able to identify these frauds in the first place because it's not seen those behaviors, and it doesn't know to capture them as fraud at all. So that will result in a lot of uh, false positives. Okay, so one of the most common types of drift here, we spoke about three theoretical definitions. The most common type of drift is input drift, right? The second most common type of drift is concept drift. So let's take an example of a concept drift that's very common. Um, let's say, and this is common not because um, it occurs this way in the real world of businesses. It occurs because of the inability of the data scientist to model correctly. So let me illustrate this. Let's say you're building a regression model, and for whatever reason, you are very comfortable with uh, linear regression. So you go ahead and build a linear regression model. One of the most you know you know damning assumptions of linear regression model is the variables are not correlated, or even if they're correlated, they are linearly correlated, right? That's the fundamental assumption of a linear regression model. So that is restricting the type of um, representations which are possible, which connect the y with an x, right? Which connect the target label with the input variables of the linear regression model. Now, you might have decided to do linear regression based representations because you know something about the domain, and the domain has told you, or you've gotten confirmation that linear relationships are what's correct. Now, as the domain evolves, or as your understanding of the domain evolves, right, which is the more common case, you'll find that the variables are not linearly correlated. So at that point, you could still use a linear regression model to do your work. It will still produce an output, which is a regressed value for that particular target column, but it's wrong. It's no longer valid because the variables underlying are not linearly related to each other, or are related to each other non-linearly. So the understanding of the data scientist of the domain, of the problem statement in the domain, evolves, and it's not that the problem statement itself has evolved. It's not that the business has changed. The data scientist's understanding has changed, and that's a scenario that's very common, especially for newcomers, especially for rookie data scientists as they learn about a domain over a period of time. So that's an example of how concept drift happens. Input drift is a lot more common because, or by far the most common, because the input data sets change all the time. So um, you might find for the longest period of time that uh, the e-commerce shopping site only sees traffic during the um, evening times, because that's when um, people who come back from work end up shopping for something. Now, uh, maybe the commerce website has now come up with a new product which appeals to housewives or house husbands or people staying at home, senior citizens, retired individuals, etc. And suddenly now the shopping behavior has shifted towards middle of the day, right? So if you went in with the assumption that I'm going to cater to people who are returning from work, you're missing out on an entire class of behaviors which are not driven by that individual, that group. It's driven by other groups. So that's an example of input drift. Okay, how do you detect input drift? Let's go about talking about automation, because we can make a lot of very interesting changes to the pipeline that we've built in machine learning, and start to work with automated ways in which we can detect some of this. So we want to basically detect changes in the distribution of the input features over time. Notice that input features by themselves can change independent of other features of the model. So that's something we need to do at the feature by feature level. So one of the most common techniques is using statistical distance measures. So there's a classical technique called as Kolmogorov's-Smirnov test. Um, Basically, you compare the feature distribution between the data that was used for training your model at that time, like maybe 6 months ago, versus the current data. And if those feature distributions have changed significantly, it's time to do something about it. The second angle that's possible, or second technique that's possible, is something called as the Population Stability Index, or PSI. So this measures the shift in the binned feature distributions. Like, what this means is, instead of calculating individual feature values and looking at correlations or looking at distribution changes, maybe those individual values are not meaningful uh, in its specificity, but they are meaningful in the group behaviors, because there's always going to be a bit of noise. So if that's the case, group behaviors can be approximated using binning. So you group a bunch of values in one bin, look at population ratios across the bins of values which are possible, because the bins are all mutually exclusive, and then see whether their populations have shifted over a period of time. And that shifting can be calculated using a specific mathematical formula, which is defined using the PSI. So if the PSI turns out to be more than 0.25, which means the shift is more, then it usually means that the input data is significantly changed, like for that feature. So that's one angle. The third angle is, of course, visualization, histograms, min-max outliers, all of that, right? Density plots. You can use all of that to look at individual features and how they have changed over a period of time. So, um, so the key thing here is that individual features, both individually as well as jointly, go ahead and monitor them, look for changes in distribution. You don't need to do this every time. Like you can do it once in 3 months, once in 6 months. You determine the frequency based on the applicability for your business. Okay, how do you detect output or label drift or target drift? So here again, you're looking at changes in the target distribution. So again, the same principles of distribution changes using statistical techniques, etc. You can do PSI on the labels. You can do Kolmogorov-Smirnov tests again on the labels. Two other specific techniques available because these are target variables, um, not the independent variables. Chi-square test. So this allows you to look at the frequency distribution of labels, so that you're not, you're working with the same type of skew that's there in the fundamental classes that are being built up. So that's one. Or you can just look at basically a way to understand proportions, like class frequencies over a period of time, especially if it's a multi-class problem. So keep tracking label frequencies, keep tracking this on a regular period of time. And if the inputs look stable and the outputs alone change because the nature of what's fraud or nature of what's a particular class is changing, then you can take the appropriate action. The third, drift, which is a concept drift, how do you detect this? So here you're looking at ways in which the relationships have changed, making your model outdated. So for this, one of the most common things that you have to track is model accuracy. But for model accuracy to be tracked, you need authoritative ground truth information about the target labels, so that you can understand what's the label that's predicted versus what's the label that's available as ground truth, and then make the comparisons between the two. So that's a crucial requirement, like for model accuracy based monitoring to happen. So keep that in mind. But if you're able to get that, obviously you have an associated set of matrices that you can track, which is AUC, recall, precision rates, etc. One of the interesting, continuous monitoring, matrices that you can track is something called as error rate. So error rate is defined as number of errors that are made in a period of time divided by the total number of predictions that happen in that period of time, right? So let's say, for instance, you're monitoring continuously for every week. Even though the model changes are expected to happen once in 6 months or once a year, every week you monitor. Every week the model makes like 100 predictions, 1,000 predictions, and the errors it makes for that week are 10, for instance. Now, 10 over 1,000 is just 1%, which is not bad, right? Maybe it's not good either, depending on your use case. But the interesting thing here is, if that 1% becomes 1.1, 1.2, 1.5, 1.9 over a period of time, like over subsequent weeks, then there's actually a general trend of increasing error rates. That's problematic, right? That's potentially indicating that something's changing underlying. In fact, I would say that it's a great way to actually understand even all other types of drifts, because ultimately it all manifests as model errors, right? So it's like a catch-all. So that's one example. That's one way to measure. The second way to measure, especially if you have ground truth again, is to build a shadow model. While you might not have promoted the I should say, while you don't change the promoted model, while you don't change the champion model, you keep building challenger models in the background. And for building challenger models, you don't need to talk to your management, or you don't need to get special permissions and all, usually, right? So you train a parallel model on that most recent data. It need not be live data. It can just be data as old as 1 week ago also, no problem. And then compare the predictions and see whether there are better models available to you, which capture the most recent representation of the two inputs and outputs. The third is using explainability tools. We'll talk about explainability tools in a couple of activities down. So the key part here is You have to keep monitoring the performance matrices of the models, especially when you have ground truth available, and also the feature attributions pertaining to explainability. So here we talk about which features are most important, most contributing to certain model outcomes. And if that changes over a period of time because new features have come up or other features are deemed to be important, it means that the model is now learning, rather the model needs to be relearned because the underlying relationships between the input and output are changed. We'll take a pause here. We'll talk about bias detection in the next video.